task here that we were discussing last week. So last week I think it was question 2 and we discussed section 8 and that's all. So today we will continue on with the other questions. Maybe wait, let me get the drawing down first. I'll just draw a quick one. Okay, we this question 1, question A. So whereby A, you are asked to find out what's the T1, U1 as well as volume. So V1. Okay, so now we will look at B. Okay, B, heat is then added to the system. So you have Q in here, causing the water to expand isobarically. So okay, this one drawing maybe a bit off here. So initially this was not in contact. Okay, so we know that. So heat added, there's no external forces here, so water will expand isobarically. This one, even if question don't say isobarically, you should kind of know this as well. So when the water fully evaporates, the piston comes into contact with the spring. Calculate the initial gap distance between the piston and the spring. So there is one small gap here. Let's call it maybe X. So you need to find out what is this X. So based on the information that's given to you here, this should be something that is quite logical. So you can see that you add heat, so water fully evaporates, and then once it has fully evaporated, then it touches the spring, right? So what you need to find out here is what would actually be the volume, actually. So the volume change, or actually to be fair, you don't really need the volume change also. Do you need? Let me see. Yeah, technically speaking, you don't really fully need it, but anyway, you still need the volume 2 for later questions, so we'll just find that. Okay, so let's see. So if the water has fully evaporated, which means that in state 2, so in state 2, the state of the liquid will be in, the water will be in saturated vapor. Saturated vapor, correct. And P2 will still be 175 kilopascal. Okay, so from here, you can actually get, so what do you need to get here? You want the specific volume, right? So specific volume will just be Vg at 175 kilopascal. change where I sit because no place to put my leg.
上面分析之前，60分。
Okay, so once you found specific volume 2, then you can find capital V2 just like part A actually. So MV2 so once you found V2, then here you can proceed to look for X, which is the gap distance. Right. So gap distance X is simply capital V2 minus the capital V1 over area, the cross-section area of the piston. Or to be more specific, just part P square over 4. This is your D. So the gap distance that you should get here, you also have the answer to this, so it should be about 4.432 meter. Okay, so then now we go to C. So C, heat continues to be added to the system until the piston rises an additional 2.57 meter. Determine the final pressure, temperature, and phase of the water. So in this case, even though we only technically one process, which is heat addition, so we actually have 3 states here because we split it into 3 different stages. So in the third state, so now in the third state, we do not know anything yet, but we do know that the piston has risen for another 2.57 meter. So meaning in this diagram here, we have additional of 2.57 meter here. Not sure what to call that, but yeah, whatever. Maybe just call it Y then. So let's say Y is 2.57 meter. That's the only thing that we know. And you need to find out what is P3, T3, and what's the state or the phase of the water. Okay, so here then you probably based on all the practices you've done so far, you probably should know what you need to do here, in this sense. So of course you can find P3 first, right? And how do you find P3? P3 will be based on what? P3 will be based on the compression of the spring, because in state 2 the piston comes into contact with the spring. So then in phase 3, if you continue to add heat for it to expand, then it will compress the spring. So then that additional pressure will be from the spring. So P3 will be equal to P1 or P2, doesn't matter, because these two are the same pressure. Then plus the pressure from the spring, or the force from the spring. So again, it's technically force, but then since area are the same, so we just say pressure. So this part will be just P1 plus Ky over area. Since we use x in B, so here we just use y, same thing. So from here, you should get the new pressure, and the value should be approximately 200 kilopascal. Okay, so stage 3, now we have one information, which is 200 kilopascal. So now we know that this is 200 kilopascal. So we have one information. We need another information, right? So like I mentioned, for every state, if you want to find out all the properties, you need two independent properties. So now it means that we need one more property here. So what do we have here? What can give you the second property in this case? So what can you give? What can give you the second property here? So the answer here is the same thing that you have been doing in A and B, meaning volume. Okay, so you can find the third volume. So volume at state 3, right? This will just be volume at state 2 plus y multiplied by A. So this will be the volume at state 3. So once you get this, then you can find out what is the specific volume at state 3. So same thing that you did for A and B, but now we swap it the other way around. Or rather, same thing that you did at B, A not so much. So this should give you about 1.585 meter cube per kg. So then from here, we get P3 equals to 200 kilopascal, specific volume 3 equals to 1.585 meter cube per kg. So now you have two information. You can go to the table. You should get T3, which is approximately 415.37 degrees Celsius. This will be at the superheated vapor table. you will need interpolation for this question. Okay, then you get T3. And here, yeah, the answer is also there. So this will be superheated vapor. Of course, I kind of skip one step here. If you want to be more accurate or want to make the answer clearer to me, then you can say that this V3 is more than Vg at 200 kilopascal, and thus you go to the superheated vapor table, then you tell me, then that's the same.
怎么是interpolation？看我不上。不一样，你看的。
Okay, so then we look at D. So D, show the process on the PV diagram and then determine the boundary work done and the total amount of heat added to the system. So essentially just find everything. Okay, so first off, you need to sketch the PV diagram first. So you get a PV diagram. This is the water, so don't forget the saturation line. Okay, so this one should be pretty straightforward. State 1, if we go back to A, state 1 starts with saturated liquid. State 2 is a saturated vapor. And lastly, we get a superheated vapor. Right, so 1 should just somewhere here. If you like to, you can also label this 175 kilopascal. And then from 1 to 2, it is a simple evaporation process. So this will just be one straight line to the right. Stop at 2. So saturated vapor. And then 2 to 3 is increase in volume, increase in pressure. So if you are not very sure how it changes, so you can also see the value that you have calculated. So V2 to V3 have increased, P2 to P3 also increases, so it's just somewhere here. So this actually would tally to 200 kilopascal. Then from here to here, because you have a linear spring, it is just a straight line. So it should look something like this. So based on this graph, then you can actually find the boundary work first, because the boundary work is just area under the graph. So which in this case, you have 2 sections here, if you think about it, because you cannot really just draw the entire thing. I mean, you cannot calculate the area under the entire thing straight away, so you need to split it into 2 sections. So 1 rectangle and 1 trapezium. So the first one will just be P1, V2 minus V1. So if you use the capital V, then you don't have to include mass. If you use specific volume, then you need to multiply by mass. So remember that one. And second part is just P3 plus P2 over 2, then V3 minus V2. So from here, boundary work would just be about this value if you calculate this. And then we can finish this off by just using the energy equation here. So this will be Q minus W equals to delta capital U. We know that this is Q in. The question also stated that, so you don't have to analyze this too much. And then boundary work is just boundary work out because it's an expansion process, actually also stated by the question. So then this is the case. And equals to delta U, so this will be M U2 minus U1. So which means, U3 minus U1, because we want the overall. So which means here, we still need to find one more thing. Okay, so back from state 3, P3 equals to 200 kilopascal, V3 equals to 1.585. You want to use the temperature also can, so it doesn't really matter. So from here, you get U3, so another round of interpolation. Okay, so you found U3, U1, part A already asked you to find, so you do have the value in part A. So then now we have everything, then you can find Q in. So this should be the answer. Just sub everything in, then you can get Q in. Okay, additional question here. For this question, can you just throw boundary work to the right and convert the whole thing into enthalpy to find Q in? How many of you think you can do that? Okay, so you can't, right? Because that you can only do that for a constant pressure process, which means that if you are asked to find the Q in for state 1 to 2, then yes, you can do it. You can do that only for state 1 to 2. But the entire process 1 to 3 you can't, because then 2 to 3 is not a constant pressure process. Alright, then we will move on to question 3. Okay, so question 3 this round for this particular paper has a lot of theory. So, Okay, so we look at question 3A first. So list down the 4 processes that a Carnot cycle consists of. So this one, in the correct order, actually it doesn't really matter which one you want to start with, but it should go in the same flow lah. So this one I won't talk about this, you can just check the notes for this. So you need the 4 processes of a Carnot cycle. So describe how the efficiency of a reversible Carnot heat engine can be increased. So the second part of this, what do you think is the answer that I'm looking for? How do you increase the efficiency of a reversible Carnot heat engine? Compressor. The first 3 words are correct, but not the compressor. So always remember this, we are still in engineering, so a lot of things can be answered just through the equations or that kind of sort of thing. So we are focusing on a reversible Carnot heat engine, so meaning we are looking at Carnot heat engine here. So what is the equation to calculate the efficiency of a Carnot cycle? So that will be NTH equals to 1 minus TL over TH. Yes, I think so. Okay, so this is the equation for the reversible. So usually thermal efficiency will be 1 minus Q out over Q in, right? And it will be equals to TL over TH if it is for Carnot. So for Carnot, you can replace the Q with T, or this one maybe if we just write Q L over QH lah, but same thing. Alright, so based on this equation, it means that we want this entire thing to be as low as possible. Right, if you want a high efficiency. Which means either you increase TH or you reduce TL. So this will also come along with like the definition of Carnot cycle. So what is the definition of Carnot cycle? Carnot cycle is the cycle, the theoretical cycle or reversible cycle with the highest efficiency between 2 temperature limits. So that was the keyword. So meaning Carnot cycle value is always fixed if you never change the high temperature reservoir and the low temperature reservoir. And it also means that just like you can see in this equation, it is only determined by the high and low temperature reservoir and nothing else. So same thing for, let's say, if you are looking at reverse Carnot cycle, so the one for refrigeration cycle. So also same thing. The only thing that will determine the COP will be the TH and the TL. Then you use the equation again just to analyze in the same way to see which one should increase, which one should decrease. Okay, then now we look at B. Water vapor enters a nozzle with a low velocity as saturated vapor at 3 megapascal and expands to 800 kilopascal. So you have a nozzle here. Initially, you have 3 megapascal saturated vapor. Low velocity, so meaning there's no velocity lah. Low velocity usually means that the velocity is not significant enough. So when it expands to pressure equals to 800 kilopascal. Okay, so calculate the maximum possible exit velocity of the water vapor and subsequently sketch the TS diagram. Okay, so for now, we ignore this term first, the maximum possible exit velocity. So we just want to see what kind of, let's see what you can do here first. Let's say you don't understand this. Okay, so of course, if you don't know what to do, write down the assumption first. That will give you maybe 1 mark. But anyway, what kind of system is this? This is an open system, right? So we are dealing with an open system here. So for your assumption, then you need the standard one would be steady operating, steady flow or steady operating condition. You can just write steady flow lah. So then the second one, no change in PE. Do not write no change in KE, okay? Because this is a nozzle. Nozzle must have change in KE. Otherwise, it can't perform what it is supposed to do. Okay, so for open system, then you can let's see. Let me see whether it makes sense or not. What I want to say. Yeah. Okay. So then we will still need this. So as usual. So just write it down first. Doesn't matter if you know how to solve it now. Let me write properly. Okay. So we know that in a nozzle there shouldn't be any work interaction. PE we also assume negligible. KE inlet is negligible. As for Q, no. The question doesn't really mention anything about in or out. So we don't supply any heat to the nozzle. We didn't take any heat out of the nozzle. So these are the one that we can cancel off as well. So ultimately, you are left with m dot h1 equals to m dot h2 plus m dot v2 squared over 2. So all this can cancel off also. Then you are left with h1 equals to h2 plus v2 squared over 2. Alright, so now H1 we can find easily, right? We know P1 equals to 3 megapascal, saturated vapor. So H1 is just Hg at 3 megapascal. Then how about state 2? So state 2, we know that P2 is 800 kilopascal. but nothing else. That's all we know, right? So for a lot of students, actually, if you don't know what to do, at least this is a stage that you should at least stop at, okay? Because all these things you can do, right? So always remember this, don't give up if you don't really understand the question. There are usually still things that you can do. Okay, so then now we go back to the question. So question actually, I mean, you'll probably be able to identify the keyword here, but then do you know what you need to do? So the keyword here will be calculate the maximum possible exit velocity of the water vapor and subsequently sketch the TS diagram. So which means that the velocity V2 will be the maximum. So meaning the whole thing here will happen under an ideal condition. Okay, the most ideal condition. So the nozzle also should be one with 100% efficiency, if you think about it. Obviously, if you don't get it, you look at B. B is also the hint because, sorry, not B, part 2. Part 2 say if the nozzle has an isentropic efficiency of 86%, calculate the actual exit velocity. So does that give you an idea on what you need to do in A? So what do you need to do in A? And in what? So if 2 tells you that if this nozzle have isentropic efficiency of 86%, then you need to calculate a new set of velocity. So obviously, the maximum velocity will be when the isentropic efficiency is 100%, right? So what does isentropic efficiency? I mean, if isentropic efficiency is 100%, it means that this is an isentropic process. So what does isentropic process mean? Entropy doesn't change, right? So which means here you can find S1. Then in state 2, you say S2 equals to S1. Okay, so if you check this, you will notice that this is actually a saturated mixture. So you need to find X2 from the entropy. So this will be S2 minus SF over SFG. And then based on this X2, you get H2. So once you get all these, then you have H1, you have H2, you can sub into this equation. V2 will just be about this value. Okay, then you need to draw the. Yeah. Can you let me finish talking? I will go back down again. You came in late also, right? Okay, so then next you can see that we need to sketch the TS diagram. So now we need to sketch the TS diagram. Okay, so same thing. This is a water vapor, so you have to remember the TS diagram. I mean, you have to remember the saturated line. So here we have two pressures, so actually you can start by drawing the true pressure line also. So the first one is 3 megapascal, second one is 800 kilopascal. So this one very straightforward actually. You started off with a saturated vapor, so it's here. So 1 is here. Then since this is an isentropic process, like we mentioned, at least we are assuming that maximum velocity, so isentropic process. So this will, okay, not so straight. So it should go all the way straight down. And then 2 is here. Okay, so just now, C, we read about the question as well, so we can actually just start with it. So C asks for the the actual velocity if you have a certain value for isentropic efficiency. So the isentropic efficiency of the nozzle is 0.86. Okay, so now this equation, since I've been using the general equation sheet all this while, so this equation is actually not in the formula sheet for this one. So you kind of need to know what it is. But then that's why it's also just 2 marks lah. But like I mentioned, yeah, don't fully trust the formula sheet. It doesn't mean that if it is not in the formula sheet, that question is not coming up. Okay, if they are not there, you still have to look through. Because usually I use the more general one. Those are for most of the questions, that's all. But of course, if it is something that's particularly hard or tricky, then I will give you the equation separately lah. But in this case, actually no, because isentropic efficiency of the nozzle is actually just V2 square over V2S. It's actually based on the velocity itself. So equals to 0.86. Sorry, this is V2S square. So it might look a bit confusing here, so let me change some word here. For the first part, this is S, okay? Because this one we are looking for it in terms of the maximum. So the first part is V2S. Then this V2S you sub into here. So then from here, you will get V2 equals to about this value. Okay, so let's look at C. So C is also another more
哪一个？
theory heavy based question. I think we can just read through. So compare and contrast the Otto cycle and diesel cycle in terms of their processes and efficiency. Provide one example of application where each cycle is used and explain the reason for their selection. So this one, I think I won't say too long here. So I will just briefly talk about it. So compare and contrast the difference, their processes. So this one, very straightforward. You just talk about what is different between these two. So it will be the combustion process. Okay, so during the combustion process, one of it is the constant pressure process, the other one is a constant volume process. So one is based on spark plug, the other one is based on the fuel injector. Okay, then of course efficiency, then this one you can talk about it. So in terms of, so if they are at the, this one maybe you can talk a bit more. So if they are both working on the same pressure ratio, so technically speaking both of them, so technically speaking then Otto cycle will have a higher efficiency. But usually we know that diesel cycle always works at a higher compression ratio, and because of that, then diesel cycle usually will have a higher efficiency. So all this we talk about them in the class, so you can look through the notes as well. So provide one example, this one you can just look through lah. So Otto cycle usually is automobile, normal car. Diesel cycle for larger vehicles like trucks and stuff, and for better efficiency, so that you can explain the reasoning as well. You can look at the notes for this.
Constant velocity.
Okay, so then we look at last question. Okay, so during winter, the outdoor temperature is at -5 degrees Celsius, and someone is using the heat pump in his room to keep himself warm. So the heat pump, working on a vapor compression cycle, is used to maintain the interior of his room at 20 degrees Celsius. The refrigerant leaves the condenser as saturated liquid, enters the evaporator at 100 kilopascal with a quality of 41.5% and exceeds the evaporator at -20 degrees Celsius. So the compressor has an isentropic efficiency of 90%, and the cycle consumes 1000 watt of power. Assume there is no pressure drop in the system. Okay, let's just draw the TS diagram first, just so we know what to do here. And I think A also asks us to draw a TS diagram, so we can draw it and note down what are the information given to you here as well. Let's see. So let's draw a TS diagram first. Okay, we note down the information. So we have the outdoor temperature at -5 degrees Celsius. Interior is 20 degrees Celsius. By now, you should be able to identify that these two are actually TL and TH. So they have nothing to do with the working of the cycle itself. These are all the external temperature, the reservoir temperature. So it leaves the condenser as saturated liquid, and so at state 3, this is still a saturated liquid, enters the evaporator at 100 kilopascal with a quality of 41.5% and exceeds the evaporator at -20 degrees Celsius. So here, maybe state 3 I don't write anything first because it's still saturated liquid. It enters the evaporator at 100 kilopascal, so the entrance of the evaporator is state 4. X4 is 41.5%, or just write 0.415. And it exceeds the evaporator at -20 degrees Celsius, which means that T1 is -20 degrees Celsius. That is the exit of evaporator. So we assume no pressure drop, which means P1 is 100 kilopascal as well, because P1 is equals to P4. So compressor has an isentropic efficiency of 90%, and the cycle consumes 1000 watt of power. So this one, we can just say that this is the work in. Okay, now we can draw this. So based on what we have here, we don't know what is the upper pressure. The lower pressure is 100 kilopascal. 3, we know that it is saturated vapor. So 4 is somewhere there. And then 1. Now, the common mistake that most students make for this question, if I remember correctly, would be at state 1. Because a lot of students will just assume that state 1 is saturated vapor. Okay, because that's the common thing that we learn in class as well. But you also need to note that for this particular question, we actually gave you a temperature for state 1. And we have pressure for state 1, just like what you see here. I noted down the information. So based on this, like I mentioned, if one state I give you both pressure and temperature, it's very unlikely that it is still in the saturated state, because saturated state, these two things are really dependent, right? So this one, if you actually check the table as well, you will see that this is actually a superheated state. I think so. Let me see. Yeah, this should be a superheated state as well. So here, when you draw this, it should start from somewhere, basically not on the, you shouldn't start on the saturated line. And since you know that the compressor has an isentropic efficiency of 90%, which means that it should go somewhere here. It shouldn't be a straight line anymore. So this one, this is 2. And maybe we note down the 2s as well. Not sure if we need to use it, but we might. So yeah. So for this cycle here, we have one work in. We have QL, then QH. So -5 degrees Celsius here, 20 degrees Celsius. Okay, we have pretty much noted down almost all the information here, so let me go get the question first. So B and C here, you can see they are just pretty much standard question. So B asks you to determine the specific enthalpy at every state, and then determine the mass flow rate of the refrigerant. Then C, determine the heating load and COP of the heat pump. Then D is the theory question. D, we'll look at it later. So for now, we need to find all the enthalpy first, and also mass flow rate and COP. What else? What's one more thing? Heating load meaning QH. Okay, so based on everything you have here, which one do you think is the logical state that you should start with? Or logical, what's the logical step here? Where should you start with? state 4. Okay, so technically speaking, state 1 and 2 also both you can do them to a certain degree. I mean, you can also find the specific heat lah. But then let's start with state 4 here. Or maybe I just reuse here so I have enough space. Okay, so from here, then it is now. Okay, so we have all the space here. Okay, so from here, state 4, very straightforward, you can find H4. Right, so this will be from HF plus X4 HFG. So state 1, we also can find H1 from the superheated table. So from here, you can get two of this value. Right, you get H4, you get H1. So which stage should we proceed to now? State 4 is there. Yeah, so don't forget, state 4 and state 3, they are just interlinked. So this one always the same thing. Okay, H3 is H4. So the issue now is state 2. We don't know anything about state 2. Right, so now our main issue, state 2, because we do not know anything about it. Then we need to start digging information from all the other states. So what do we know here? Like what can we find out? Which state can we make use of here? Isentropic efficiency won't be useful for you at the moment. It will be useful like slightly later. But yeah, that's also one of the things that you need to know. So from which state can we get some form of information here? Yes, so that one is for 2S. Okay, so one obvious choice here will be state 1. If you get entropy of state 1, then you know that in state 2, S2, S is S1. Don't forget that it's always S2, S. This is not S2 yet. That one later we can make use of the isentropic efficiency. Now, so this one information. So how do we take out the second property here? We need another property. So another thing that we know about this state is this, right? So which means we can go back to state 3. State 3, we found out H3 equals to H4, but one more thing that I never write out from the question is that state 3 is actually saturated liquid state. So which means from here, you actually have two properties. You can find P3. So this P3 value should be approximately 1000 kilopascal. I purposely chose the quality such that the the H3 and H4, it will give you 1000 kilopascal here lah. Okay, so which means then from here you get 2 information for state 2. And then for state 2, then through interpolation you can find H2S. Then you can make use of isentropic efficiency. So this one is just H2S minus H1 over H2 minus H1. And this will give you H2. Okay, so now then you fulfill all. We have H3, H1, H2, H4. So we can move on to the next part, which is to look for the mass flow rate. So to find the mass flow rate, of course, the only thing that will give you the information of the mass flow rate will be the work in here. So we know that work in is equals to F dot H2 minus H1. Don't accidentally use H2S instead. It is always a H2. And this is equals to 1000 watt or 1 kilowatt. So then from here you can get the mass flow rate value, which is approximately this.
情况无法应用到本身。对，读号。
Okay, then let's quickly finish this up. So then C is just the heating load. So heating load is essentially QH. So this is just m dot H2 minus H3. And then COP for heat pump is just QH over work in. So this should give you approximately this and this 3.4. Yeah, because divided by 1. Alright, then we move on to D. So D is a very straightforward question at first as well. So compare the COP from C, which is what you have just calculated, with that of the reverse Carnot cycle. So you obviously, if you want to compare, you calculate it first. Okay, so you calculate the reverse Carnot cycle COP first. So for a heat pump, then this will be 1 over 1 minus TL over TH. Okay, so once again, remember to convert the temperature to Kelvin. Don't use degrees Celsius for the calculation. So if you calculate this, you will get about this value. Okay, so if you compare those two, then you will obviously see that the reverse Carnot cycle COP is higher than the actual COP that you calculated. So then maybe you can explain a bit. You can use two ways. If you use the actual COP, you can say that the actual COP is lower because the performance is not as high due to irreversibilities. If you choose to use the reverse Carnot cycle side to explain, then you can just say that because reverse Carnot cycle will have the higher COP between two temperature limits. So no actual cycle will have a higher COP. That's why the COP is higher here. So that will be for comparison. So explain how the heat pump's performance is affected if Clive chooses to maintain the room at a higher temperature, more than 20 degrees Celsius. So this year's question maybe in some way is not as good because this is actually a repeat of question 3 if you think about it. Which means that if you don't understand question 3, you probably cannot do this also. What I mean is this, because question 3 I asked how do you change the efficiency of the Carnot cycle, right? And there is true change in T. So this actually use the same concept, right? So if he chose to maintain the room at a higher temperature, you can actually just use like this equation to explain. So if the room is at a higher temperature, which means TH is higher. If TH is higher, which means that this entire thing is lower, but I go one by one. So TL over TH will be lower, which means 1 minus this will be higher, and ultimately this is lower. So meaning, if he chose to maintain the room temperature at a higher temperature, then the COP of the heat pump will actually drop, resulting in a worse performance. Meaning, yeah, a lower COP, essentially. Oh, reversible. reverse. It's reverse Carnot cycle. No, it's reverse. So anything that you want to ask me here? Okay, so now discussion of past year will stop here. It's not like we have time for more papers. Okay, now maybe before we end the class, I will show you. Actually, not to say. Of course, no. Of course, the video actually has been uploaded. I will just show you some kind of revision video. It's just that. No. It's just a recap. No, actually, I always meant to show this video after after I finish teaching all the chapters. It's just that back then I forgot, so I jumped straight into past year. So it's just a revision for the first half of the lecture lah. But not video made by me. It's just some random YouTube video.